This video is sponsored by Brilliant. In the last video, we introduced different intermediate representations. So the program is now made of flat instructions and every variable is assigned exactly once. That setup on its own didn't make the program any faster, but now that we have it in this form, the compiler can finally ask the questions optimization actually depends on. And that brings us to one of the most exciting stages of the compiler pipeline: optimizations on the intermediate representation. Hi and welcome to Premature Abstraction. This is part 7 of building up the complete picture of how compilers work. And today we've reached the optimizer. We'll go through the optimizations a compiler performs on the IR, the ones that turn a literal translation of your source code into something that actually runs fast. If you recall, we already did a video about optimizations on the AST. But now the program is in a different form, which is way better suited for optimizations. This form is static single assignment. Every name has exactly one location where it's defined, so the question, where does this value come from, is trivial to answer. Many data flow questions that would have needed complex analysis on the AST become a single lookup on SSA. Constant propagation just becomes look up the one definition, and that code elimination becomes find names with no users. Second, we have the explicit control flow graph. The IR groups its instructions into so-called basic blocks, which are sequences of instructions with no jumps in the middle. Therefore, these blocks will each be executed as a whole, and the edges of the graph are the possible jumps between them. On the AST, control flow is implicit in the nesting of if statements, loops, and functions, which makes analysis a lot harder. But on the control flow graph, reachability is just a simple walk. Together, these two changes are pretty much why every optimization in this video is either dramatically easier or only possible at all here. Beyond the cleanups that we've already seen, like constant folding, constant propagation, and that code elimination, there's one more worth naming. If two instructions compute the same expression, we don't need to compute it twice. We can compute it once and reuse the result. That's called common sub-expression elimination. On SSA, this generalizes to global value numbering, which identifies values that are provably equal, even when they came from different SSA names. So if v0 equals a plus b shows up in one block, and v3 equals a plus b in another, GVN gives them the same number, and the second collapses into a reference to the first. We can also sort operands, so b plus a becomes a plus b, which is called canonicalization. And so we catch the commutative cases too. Once we have the explicit control flow graph, a whole new family of optimizations opens up. First, jump threading. If a block jumps to another block and its only job is to branch on a condition we already know, then we can just skip this block entirely. And tail merging. If two blocks end with the same instruction sequence, merge their tails into a single shared block. Also, we can better detect dead code. For example, through branches whose condition is provably false, loops that will run 0 times, and blocks that are reached by no edges. The interesting part is that control flow cleanup and data flow cleanup feed each other. For example, if you remember phi nodes from last video, removing a branch can collapse such a phi node into a single value, which exposes a new constant, which might dead end another branch, and so on. There is a pass called sparse conditional constant propagation, or SCCP, that combines these two ideas into a single fixed point computation. And it's strictly more powerful than running them separately, because every elimination can reveal new ones. Programs spend most of their time inside some loop, so this is where shaving instructions really pays off. Let's go over a few classic transformations. Say there's an expression inside a loop that doesn't depend on anything that changes per iteration. It just gets recomputed every time with the same result. We can hoist it out of the loop and compute it once, which is called loop invariant code motion. If a loop body is small and the bookkeeping per iteration, like incrementing the counter, jumping back, etc., costs as much as the actual work, we can duplicate the body a few times so each iteration does the work of several, or just duplicate the body without looping at all. That's loop unrolling. If we have an if inside a loop, whose condition doesn't change between iterations, we can lift it outside the loop, which is called loop unswitching. Say two loops run over the same range, doing different things on the same data. We can merge them into one loop that does both, so-called loop fusion. The reverse, called loop fission, is also useful. We can split unrelated computations into separate loops, which can, for example, help a vectorizer notice potential optimizations. And then there's loop interchange and tiling. Iterating a 2D array column by column instead of row by row can be many times slower, because each axis jumps to a different cache line. Loop interchange swaps the loop order, so axes run sequentially through memory instead. Tiling does the same kind of thing in blocks, for cases where the working set is too big to fit in a cache all at once. These cache-aware transformations can be the difference between a loop running at memory speed and a loop running at cache speed, often orders of magnitude. This is the first time in the series the compiler's reasoning about actual hardware, like cache lines and memory locality. The IR is still target independent, but the heuristics here are already shaped by what usually runs well on real CPUs. Before we continue, a quick word about today's sponsor, Brilliant. In this series, we're always talking about handing work off to the compiler, but for learning, the opposite is a lot more effective. A student today can have any answer generated for them in seconds. And the struggle that gets skipped is exactly where they would have actually learned something. Brilliant's answer to that is Koji, their new tutor, and he's built to help you around that. He won't just hand over the solution, he asks smaller questions until the student arrives at it themselves. We just talked a lot about loops, and on Brilliant there is also a computer science lesson on nested loops, and my program ran completely past its goal. So I asked Koji what went wrong.
What condition would make it stop as soon as it finds a gem?
Notice that he didn't just fix my code, he made me retrace what the inner loop was actually checking, and by the time he was done asking, the fix was obvious to me. What got me was that his question reacted to my specific mistake. Koji works this way across everything on Brilliant: math, science, computer science, and it's aimed at students from 5th grade through college. So this is the closest thing I've seen to a one-on-one tutor that's simply always available, no scheduling, no logistics. I genuinely wish I could have learned this way back in school. Click the link below or scan the QR code to get started with Brilliant's tutor for free. You can upgrade to Premium to unlock all courses, and right now you can save 20% off an annual subscription at brilliant.org/premature abstraction. Thank you to Brilliant for sponsoring this video, and back to compilers. A well-known optimization is strength reduction. Replace an operation with a cheaper one. There are a few famous examples, like doing addition or bit shifting instead of expensive multiplication or division. Although it is important to know that on modern CPUs, multiplication is still fast, so the wins here are often modest. The more interesting form happens inside loops. When you write a indexed by I, the compiler lowers it to address of a plus I times the size of one element. That multiplication runs on every iteration, but the index just increments one by one, so each iteration's address differs from the previous one's exactly by one element. So instead of recomputing the whole address, the compiler can just keep a pointer that gets bumped by the element size each step. And so a multiplication per iteration becomes an addition per iteration. Following that path further, we arrive at the most relevant single optimization in this video, auto-vectorization. Modern CPUs have SIMD instructions, single instruction multiple data, which can do the same arithmetic on, say, 8 numbers at once. A scalar loop that adds 2 arrays element by element can be turned into a loop that adds 8 elements per iteration in a single hardware instruction. The compiler does this automatically with no help from the programmer. Or rather, it does it when it can prove a long list of conditions, that the arrays don't alias each other, that the number of iterations can be computed before the loop starts, that there's no early exit, that the alignment is right, that no iteration depends on a previous one. That last one is the most common hard deal breaker. Something like this can't vectorize, because lane 1 needs lane 0's result before it can run. And when a condition fails, the code falls back to the scalar version. This is one of the reasons why 2 loops that look very similar in source code can have a wildly different performance, simply because one of them gave the compiler enough proof, while the other didn't. Of all of those conditions, aliasing is the one that comes up most often. Almost any rewrite that touches memory has to answer the same question first. If I move this load earlier, or skip this store, or reuse a value that I loaded a moment ago, could some other pointer in between have written to the same place? That's what Alias Analysis answers, and it comes in many flavors. The cheapest one needs no language guarantees at all. 2 separate allocations are 2 separate objects, and a local variable whose address is never taken can't be reached through any pointer whatsoever. Then there's the type-based flavor, which leans on the promise the language makes. C says you may only read an object through an expression of a compatible type. So if a program writes through a float and then reads through an int, that's undefined behavior, and the compiler is free to assume it simply never happens. But real projects do this constantly, which is why projects like the Linux kernel build with the no strict aliasing flag. A different angle is tracing where each pointer actually came from, which is points-to analysis. If p is the address of a local that never escapes the function, and q arrived as an argument, they can't alias, whatever their types. Once aliasing can be ruled out, a bunch of nice things become legal. A load from an address right after a store to that address can use the stored value directly, skipping the load. Or two loads from the same address with no store in between can be collapsed into one. And if an allocation never escapes the function, it doesn't need to live on the heap. The Ghost compiler moves it to the stack, while the JVM often dissolves it entirely, replacing the object with plain fields and registers. Sometimes the programmer can also answer this directly for the compiler, saying, "Trust me, these don't refer to the same memory." C has the restrict keyword and LLVMIR has no alias. But the compiler doesn't verify these, it just believes you. So mistakes here can cause issues that are hard to debug. Remember from the last video how lowering to the IR makes a lot of things explicit that were invisible in the source, like bounce checks, null checks, overflow checks. We would expect that to make the resulting program slower, since on paper it has to do more work. Take a simple loop summing an array, something like this. At the source level, every array access starts with an implicit bounce check, even though we know that I will never be out of bounds. After lowering, the check becomes an explicit branch in the IR, sitting right next to the loop's increment, and it's I smaller than the length of the array condition. Range propagation can now prove that I is always between 0 and the length of the array, so the branch is provably never taken, and the bounce check disappears. But removing hidden work is only half the story. Lowering also removes the lines between source level operations, and that lets the optimizer combine pieces of one instruction with pieces of another in ways that the source couldn't express. Looking at the same loop, each array access lowers to base plus I times 4, as we've already seen. This is now sitting in the IR right next to the loop's increment of I. In the source code those were unrelated, but in IR they are just sequential operations on I. Induction variable analysis now spots that I advances by 1 each iteration with a known stride, and strength reduction uses that to merge the multiply with the increment into a single pointer bump. So in the end, half of the indexing operation and half of the loop increment have been merged into one instruction. Before we get into the last few ideas, I want to take a quick moment to thank everyone supporting the channel on Patreon. You're the reason this series can keep going, and I really appreciate it. If you'd like to join them, the link is in the description. Many optimizations are not possible because the compiler can't prove that the code was pure, that it had no side effects. Take something as simple as calling f of x twice with the same x. If f is pure, the second call is the same as the first, and the compiler can replace it with the result of the first one. But if f has a side effect like writing to a global file, printing something, or reading a file, the compiler has no choice but to call it again. Almost every optimization in this video has some version of that question hiding behind it. This is exactly why functional languages have a real advantage here. In a language like Haskell, purity is the default. The type system tells you which functions can have side effects, and everything else can be optimized freely. The optimizer can reorder them, deduplicate them, pre-compute them, evaluate them lazily, all without risk. Imperative compilers instead have to spend lots of work inferring purity from the code. GCC has function attributes called pure and const that tell the compiler, trust me, no side effects, no observable state. Also, modern compilers infer the same property themselves wherever they can. Overall, we can say that purity is like some kind of universal currency for optimization, enabling it when it can be proven. Most of what we've discussed so far operates on a single function and sometimes on a single basic block. There is a category of optimizations that take a step back and look at the bigger picture. The first is function specialization. If a function is often called with the same value for one of its arguments, the compiler can clone the function with that argument inlined as a constant. Constant propagation can now do its thing, simplifications cascade, and the specialized version often shrinks quite a bit. This is a close cousin of a technique that we already saw, inlining. But instead of pasting the body at the call site, you keep a separate specialized copy that all matching call sites can share. A general rule is that the more context the compiler has about the program, the better it can optimize. So there is link time optimization, or LTO, where the linker reruns the optimizer with the whole program visible. Now the optimizer can see across files, and inlining and specialization work across file boundaries. And finally, Profile Guided Optimization, or PGO. You compile the program once, run it on real workloads with profiling enabled, and then recompile using that runtime information. The compiler now knows which branches are hot, which functions are called the most, and generally which loops dominate the runtime. It can inline more aggressively where it matters, and lay out code so the hot paths sit contiguously in memory. This is also the natural transition to just-in-time compilation, which we can get to in a future video if you're interested in that. Just like the AST stage, there are some optimizations on the IR that technically preserve the as-if rule, but quietly change something the programmer might have been relying on. A common one is FMA contraction. A multiplication followed by an addition gets fused into a single multiply add instruction. That means that the floating point number gets rounded only once instead of twice. So different bits appear in the result. The C standard permits this by default, even without any fast math flag. Another is when range check elision hides bugs. An out of bounds read might fail loudly at 0 with the check still in place, and silently return garbage at 02 because optimization removed it. So the bug was always there, the compiler just changed if and how it surfaces. A while back, there was a benchmark making the rounds on social media that claimed to compare the speed of different programming languages by running each of them through a nested loop. It was generally taken apart because the benchmark wasn't really measuring nested loops at all. It was measuring integer division because that one instruction in the inner loop dominated everything else. Whatever the benchmark thought it was measuring, the numbers were really just telling you something about how each language's compiler handles idif. But after this video, you should now have the vocabulary to understand why. A loop you wrote to measure one thing can easily end up measuring something else after the optimizer is done with it. The divide became a shift. The loop got vectorized. The unused result got eliminated. The constant argument got specialized away, and so on. Even slightly changing your benchmark code can, for example, cause the optimizer to not recognize a pattern anymore, which puts this test at an unfair disadvantage. Most micro-benchmarks have some version of this problem, and the optimizations in this video show a big part of why. And that's the optimizer. It's an essential part of any compiler, and the reason the programmer can focus on the code architecture, instead of trying to prematurely optimize it. But even after all of this, there are still things the compiler hasn't done yet. Until now, we've been working with an unlimited pool of virtual registers. But of course, the actual machine has a fixed number of registers, so this needs to be resolved. We haven't talked about instruction pipelines, latencies, or which instructions can run in parallel yet. And we haven't picked specific instructions from a real instruction set. All of that is the backend's job, and it's where we go in the next video. This has been Premature Abstraction. Thank you for watching.